All right. So again, this is Yajun. I'm the chair of the Women Engineering for IES. And now let me introduce Dr. Qing Tang, who will give a talk on transforming manufacturing with AI. Um, so Qing had her PhD degree from electrical and computer engineering from the Graduate School of Electrical Engineering at the University of Ulsan, South Korea in 2022. She currently serves as a senior researcher in the data analysis team at INTERX, a leading AI solution provider for the manufacturing sector in South Korea. Her research focuses on intelligent manufacturing systems, advanced surveillance, and transportation systems, with a particular emphasis on the application of computer vision and machine learning techniques. So Qing, you have the floor to have 30 minutes presentation. Thank you.
Thank you. Thank you for the introduction. So I'm going to dive into my presentation. Yes, so good morning, everyone. It's truly an honor to be here today. I would like to thank Professor for inviting me to speak at this Women in IES session and celebrating the IEEE IES Day. So today I will going to share my insights from my team's work under the topic transforming manufacturing with AI from data analyst to the smart factory. So in this presentation, I'm going to talk about how AI can transform traditional manufacturing into what we call a smart factory. So I'm going to share 6 key solutions that our team built and the use case our team research on and working on. These examples will show how the AI can solve the real problems in manufacturing and improve the factory's efficiency, accuracy, and adaptabilities. Okay, before we go into the details about our research work, let me introduce myself briefly. So from 2011 to the 2015, I studied mechanical automation for my bachelor, and then at Shanghai. And then after that, I'm going to start my PhD degree in electrical and computer engineering at the University of Ulsan in South Korea. After I finish my PhD, I start to think deeply how I can apply my research and knowledge to solve real world challenge. So it leads me to focus on real applications of AI and technology in industrial. So that's why since 2022, after I finished my PhD degree, I started to work as a senior researcher in the data analysis team in INTERX, South Korea. With my team, I have been research and exploring how to transform traditional factories into real smart factories. Now I'm going to introduce my company a little bit. So my company and my team is focused on the industrial AI and autonomous factory solutions with a vision to develop easy-to-use industrial AI service. So our vision is how to make our AI easy to use, and then what AI application is our clients really want. Our research area includes the manufacturing AI and manufacturing DX platform service. Also, we have the office and the AI research in research labs in South Korea and a branch in Frankfurt, Germany. Yep. And for actually, every client, they trying to ensure the product quality, and the production always is the most important things for manufacturing. So therefore, at the very beginning, we start to optimize the product conditions and then quality predictions and analysis from the 2020 to 2021. And then in 2022, our team launched the Safety AI, which can provide a real-time solution for the human safety in factory. And then luckily fortunately, as the large language model become popular in 2023, and we at the same time we began to research in manufacturing specific LLMs at the same time. After more than 1 year's research and development, we launched the document AI for industrial document parsing, and then following by that, after we have the document parsing, we have all the information, and then we also launched the Gen AI industrial domain specific chatbot service. Okay, so I'm going to introduce what is the smart factory first. Traditionally, we have level 3.0 manufacturing, which means the central on automation. But right now, we have a lot of development in AI technology. The next step is level 4.0 for how to combine the automation with AI. It means the machine not only can operate automatically, but also can learn and then make some prediction and decisions by machine itself. So all the things are about to make the manufacturing faster and then more efficient and more high quality, much more high quality products produced. And then about the all the thing is about the human safety in the factory. Yeah. So and then after I introduce what is the most important, what is the smart factory, and then we need to go into think why is the smart factory is very important. Yeah, so first we going to look at some common problems in traditional manufacturing. First, we can see the production actually always slow. The human a little bit slow because the human you need to take a rest, and sometimes you need to make a decision. But for AI, it can help and assist the person to make the decision. That's why traditional setup cannot always meet high production needs efficiently. And second one is there's not many skilled operations. The training of skilled workers is always take a long time, and then it's very cost a lot of money, and and the third one is equipment faults have the issues. So machine need to continue supervision by humans sometimes. That's why we're thinking about how about we supervise the machine by AI technology to prevent breakdowns, and that's why that can alarm in the anytime if the machine broke down, the AI will make an alarm to the factory to there have an issue in here. You need to make some action to fix these issues. Yeah, so all of our solutions are built to solve these problems. Yep. And then from now on, let's go dive into some really specific solutions one by one. There are some challenge with the on-site data. The first challenge is the data gap between the research and actual factory conditions. The data from the public data sets cannot be used in real data in real factory environments. And then another issue is the limit defective data available for training the AI model. And moreover, there's no even have one label in defect samples. So based on these challenges, we can say how to avoid these issues. Based on this one, we trying to tackle these issues. That's why first we design to optimize production conditions, predict and analyze quality in unsupervised manner. Yep. And then we start with the input data set, which includes the measurements like current and temperature and others informations like equipment, setting venue. And then all of this data cluttering is the intervals is different. Sometimes we plot the data because of the sensor type. Sometimes the data is collected from in 100 milliseconds. Sometimes the data is collected in 1000 milliseconds. That's why to ensure the consistency between the data dimensions, we need to pre-processing the data using average pooling or the others normalization technology. And then after all the data goes to the same standard, the CNN autoencoder encoders this time series data or no time series data is okay too, to extract the key features, what is the really important features in the data. And then the model will trying to learn and then trying to learn to reconstruct normal signals. So when a new data, we have the AI model, after we have trained it AI model, if a new data comes in, it will have a significant difference. It will have a large difference between the new data if this data is a defect data, because we train the model using all the good data. If the very different data, it means the defect data come inside, we can observe this is a really large gap we can see. That's why we can, the model will say, okay, this is data is a defect data. This is the example result of our model. And then this model simulates both good samples on the left side and the defective samples on the right side. In the output, defective samples show it's a really large gap from the model prediction in red line, and then the origin, it means the actual data. This actual data maybe is good data or maybe it's a defective data. Yes. So if the gap is large between the prediction data and the original data, the model will say this is a bad pattern. We can say this is a defect pattern. And moreover, compared to the good samples, our model can help us to easily identify the time, and then we can say which position of the defect is happened. We can see, for example, like in 500 microseconds, there have defects happened. Yeah, and then after the data domain, we can go into look at the inspection AI. This is a little bit different. This is the image-based AI model for product quality inspection, and especially useful when we have imbalanced data. I'm going to introduce two models we use. And the same challenge is faced in the image processing, just like the data processing as well. And it always have a gap between the research public data and the real conditions. Actually, in my about 5 years experience in this field, I can say like 90% of the data is not from the public data set, is we collected by our staff ourselves. That means that it is really have a big gap between the research data and the real conditions. And then second one, yeah, is the same. We always have the limit defective samples, because you can imagine like if a company, if a factory, they always have the defect data, it means their product actually is not good. So always have the 99.9%, more than 99% data is good data, and then only maybe 0.1 or 1% data is defect data. So collecting defect data, it takes a long time and it's very difficult. And then the last one is defect. Sometimes it's unknown. It means that defect is a new type defect. We didn't see this defect in our training set. If that is really make the AI model can confuse. AI model cannot classify in the real new type. Is not good at predict. The AI model always predicts what he already learned from the training sets. But if the data it doesn't have the same pattern in the training set, the AI models will confuse about that. Yeah, so that's issues we met currently in our real world data in our real world project. So the first approach is very simple. For handle the imbalanced data set, we trying to split the process into the two steps. The first one is detection, and the second one is classification. Most of the detection models already have the classification functions, but in our data set, as I said, detector is actually, because the data set is very imbalanced, the detection and is very harder to augment defect data set. And then, but inversely, the classification data set is very easy for data augmentation, and it allowed us to generate many, we can say fake data, fake synthetic defect image for training. That's why we separate the detection and the classification, actually the same step into two different steps. Yeah, and then the second approach is we trying to use anomaly detection in our most of cases, in our most of projects because as I said, there is no many defect data. We need to use all good data to train the model, and then when the defect data come in, our model will directly compute how many distance between the good data and the trended good data and then defect data. So if the gap is very big, the model we say, oh, this data we didn't see before, we didn't see the same pattern in our good models. That's why this is a defect. Yeah, and then our model is designed this with a very strong focus on the model's reliability and accuracy. Unlike the previous many research paper, they actually rely on loss function and the loss value to select the best training epoch. Because in the real world scenarios, we don't have defect samples, as I said many times. And then that's why we don't have label. We don't have label. It means we don't have loss function. We cannot compute the loss function. It means we don't have any loss value. We cannot observe the loss change. Yeah. So if our loss function always change a lot, just like the next page in here, we can see the baseline, the baseline, the loss function, and the accuracy change a lot during the whole training AI training process. It means if we stop our model in some epoch, maybe unfortunately we will get very bad performance model. It means the model is it means we can get if our model perform like this way, it will be very dangerous. Yeah, that's why our model trying to focus on reliability and accuracy. And for produce a very stable loss function, we propose a loss function in here we call the HCL loss, hardness aware course entropy loss, to fix that. And then our experiment is shown in the second line. You can see with our proposed HCE loss, the model accuracy goes to stable. So we can stop the training as what we want at any time, and then the model accuracy, model performance can stay like always 90%. And but for the first figure, if we don't use the HCC loss, we proposed one. And then if we choose in very bad, unfortunately, maybe our model accuracy will suddenly go to the 30%. Yeah. And then let's go to the human safety part. Here is our safety AI solution. It's a real-time solution for the industrial safety environment. And then we have several key functions. The first one is safety zone monitor to ensure the workers stay within the safe area. If there's a area is not safe, and then the person go inside, there have some signal. We go to the manager, and then the manager can check the real time, can check the environment in real time. And then second one is worker identity and time check-in. The checkers who will on site, and then they will go into check-in on time, and then if they check in without typing any information, we use the face recognition technology to achieve that. And then the third one is activity detection. And right now we already have the fall down detection. If a worker fall down and then slide down, the alarm will, the detector, it may have some, we can say, accident. for prevent this accident, we will also we need to detect these abnormal activities, and then yes, and the last one is if the last one is if the person go inside the unsafe zone, we need to control the robot to stop the robot arm if the person just break into an unsafe area accidentally. Yeah, and then we can say for our last use case actually is finally goes to large language model, and everyone is very interested in here in this field right now in these 2 years. The first we need to I will going to introduce the documents passing. The document passing is very basic and initial step for applications like retrieval argument generation. So the large language model can our document AI can autonomously produce and then process the documents, make it very fast and more efficient. Why we need this one is because when human read a document, we can easily understand what is the meaning on there. But if we trying to get some information using the AI, we need to using the image processing technology. That's why the document parsing converts these complex industrial documents into the computer recognizable files. And then the computer and AI, we can say, can use this information to train, can use this information to assist the worker, and then can use this information to train generated model like the large language model in the later. And then in the other words, before we trying to use some information in our documents, we need to know how to extract information from these documents. That is why we provide this solution with our manufacturing specialized chatbot and assistant solutions generation AI. Yep. So let's go to the detail in our document AI. The document AI the industrial document have some features. We can say they always have a lot of intensive domain specific knowledge. And then if we don't have this domain specific knowledge, the normal person will not understand what is talking about in this document. And this document always have many complex formulas and then structured data like tables. And that's why we design our document AI architecture like in this way. We didn't define an end-to-end model. We're trying to separate all the model one by one. First, we start from the layout analysis to understand the document structure. And then after we have the layout, we break down a PDF file, or we can say a scan file, into components, just like tables and images and formulas and tests. And then as I said, there have lots of formulas and they have a lot of tables in our document, in the industrial document. That's why the specific model like a formula model and then table model is individually adapt after the layout analysis done. Finally, we need to sort all the data. We need to sort all the results and then sort the result from table model and then result from the image model, result from the formula model, and then we need to merge all this information again, and then rendering this information to a new computer readable documents. Yeah, finally, so until now, we can extract any data we want, and then we can extract any data the client want to use. So right now we can go to train our we can go to build our generative large language model using this kind of data, all these data. And then our generative model, our large language model, Gen AI, is combine the RAG to generate many information from the last document. Because as we know, the large language model take a lot of time for training. Some large language model take maybe 1 month, and then sometimes it's 3 months. So it means we cannot train the data when we get a new, we cannot train the model when we get a model, when we get the data at once. That's why we trying to combine the RAG with the large language model together. For a large language model, we fine-tune the open source model to generate manufacturing specific to help worker and to generate some natural language. And then for the very secret documents, we can say that document cannot send to the large language model. So we will extract the information from these documents and then save to the dictionary using the RAG technology. Okay, so finally, I'm going to show you a video of our on-site platform in action. This video will show our solutions. I introduced 6 solutions of our teams. And then this video, we're going to show all of our solutions on-site and give you a very closer look at the processing on the factory. It's about 1 minute. In here, the data will go to the standard. We also have the digital twin, but since I'm focused on AI, that's why I didn't present the digital twin part in here. I think we can stop in here. Yep. So now is the last page. If you have any questions, you can ask me at this time, right now. Thank you for listening.
Thank you, Qing. Thank you very much for your presentation.